All right, so we're going to start off today looking at substitution reactions of alcohols, and luckily we've seen a fair number of these reactions before, and then I'll introduce some newer ones. So let's do some review first. We've already seen SN1 reactions involving alcohols, and we know in order for an SN1 reaction to occur, you have to have a highly substituted carbon. Ideally, you want it to be something like a tertiary carbon with an alcohol coming off. And we can easily swap this with the bromine using what reagent for SN1 chemistry? HBr, right? If we think about alcohol, the OH here is a really crummy leaving group. However, if we throw in HBr, the hydrobromic acid will quickly protonate that OH group. It'll fall off, form a tertiary carbocation, and then your conjugate base, that Br minus, can attack back in. So that's really simple, but like I said, you have to have a highly substituted carbon, either secondary or tertiary. Primary carbons just really don't do SN1 chemistry. All right, and then SN2, covered that last term as well. You know SN2 chemistry is more likely if you've got a less substituted carbon, like a primary carbon, with an alcohol on it. And what if I want to switch off this alcohol for a bromine? What could I do? Again, we're running into this problem where this is a crummy leaving group. What are the two ways we have of converting it to a good leaving group?
Tosyl chloride.
Tosyl chloride and pyridine, that was one way. That tosylates the alcohol, and then what can we add to swap off that tosyl group with the bromine? NABr, right? Because we want that Br minus to do the attacking. So NABr would work well for that. That works. All right. Another method we could use to accomplish this exact same goal, instead of tosylating it, is to protonate it, right? So if we do this, we can still use HBr. We first protonate it, so let me show the full mechanism down here, and then we'll take a look at it. This mechanism is different. Your bromide's just going to attack the backside, kick that off, and you'll end up going to the final product. So it looks a lot like the SN1 reaction. However, the steps are different, right? SN2, we never go through a carbocation. We just have our bromide attack the backside and kick off our water. And this does work for simple alcohols. Does that make sense? So it won't form a carbocation, right? So if we look at this SN2 reaction, do you notice how the water didn't fall off and then the bromide attacked in? It happened in one step. And that's what differentiates SN2 versus SN1. I was saying with SN1, you have to have a relatively stable carbocation, which limits it to usually tertiary systems. So a little bit of review from last term. All right. There's also a couple other different routes. All of these that we've seen so far work for installing bromines, but then the question is, well, what if we want to do this and install a chlorine? Usually people will say, well, can't you just do HCl? Not quite. The activation energy is just a bit too high. So what you have to do is you have to add in zinc chloride in order to help this reaction swap out your alcohol for your chlorine. This essentially acts as a catalyst for the system. And the reason for that is we know the chloride anion isn't the world's best nucleophile, so we kind of have to amp it up a little bit. I'm going to put a big disclaimer on this, though. Zoom out. Say this only works for water-soluble alcohols. If you've got a big, long, greasy alcohol, this reaction won't work, and that's because zinc chloride isn't soluble in really anything but water, and so we are limited in that regard. All right, one thing to watch out for is if you are doing the protonation chemistry and we have a secondary carbon, you could run into rearrangements. We've seen rearrangements a lot already, so just always watch out for rearrangement chemistry if that can occur. I did want to show you some new reactions though. So let's take a look at some new methods. The first one still starts with a simple alcohol. And our goal is to go and swap that out with a chlorine. Like I said, you can use HCl and zinc chloride, but that really limits you to small alcohols that don't have big, long carbon chains off of them. This one works with practically any alcohol. And you use something called thionyl chloride, or SOCl2, and pyridine. And this swaps off your alcohol for chlorine, and I'll show you this mechanism shortly. The second one uses phosphorus tribromide, so PBr3, and we can use this to swap off with bromine. Another note is both reactions are SN2 reactions. So watch out for inversion. Oops, that R doesn't look very good. There we go. We saw last term that anytime you do SN2 chemistry, you're flipping your electrophile inside out like an umbrella flipping inside out. The same thing happens in these. So if you do have a stereocenter, you're going to invert that stereocenter. So let's take a look at the thionyl chloride mechanism. That's that first one with chlorine. It's a pretty neat mechanism. We're going to start out with our alcohol. And like I said, alcohols don't do substitution chemistry because they have bad leaving groups. So the whole goal with this mechanism is to convert this OH into a better leaving group. And thionyl chloride is a sulfur-containing compound. Looks like this. And this is a really, 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 really good electrophile. It wants to be attacked by a nucleophile. So if it's a good electrophile, this oxygen can quickly attack that sulfur, kick up electrons onto the oxygen. You end up with an oxygen that has a negative charge coming off the sulfur, and then the oxygen that attacked now has a positive charge. In the next step, this oxygen will really quickly clamp down and kick off chlorine. We know chlorine can be nudged off pretty easily because it's a good leaving group. We reform that sulfur-oxygen double bond, and we have a positive charge here. And we still have our leaving group that was chloride floating around. And then next, what happens is that pyridine solvent helps neutralize that oxygen with the positive charge. So if you remember, this is what pyridine looks like, that PYR. It's a weak non-nucleophilic base, so it's going to pluck off this proton, and we'll get to our neutral product. And we still have that chloride floating around in solution because this is a one-step reaction. Does that make sense so far? Kind of complicated? In the next step, the chloride with the negative charge is going to do our backside attack. We're going to clamp down, and we're going to kick off chlorine all in one go. So if you remember, this is an SN2 backside attack by the chlorine, because all of a sudden, whoops, this is a good leaving group. And let's take a look at why it's a good leaving group by assessing our products. If we look at our products from this reaction, let me be thorough and include the pyridinium salt. This product right here is a gas. Leaving groups that, when they kick off, decompose into a gas are really, really favorable. If you remember back to general chemistry, you guys probably talked about Le Chatelier's principle, right? If you're developing a gas in the reaction, it actually favors formation of your product, generally. So in this case, by forming sulfur dioxide gas, you're pushing the reaction to completion in this last step. It's a really, really downhill reaction and highly spontaneous. Does that make sense? So it is a bit complicated, but it's a very useful reaction. And like I said, it's important to remember that because this is an SN2 reaction, you do have to watch out for inversion of stereochemistry. All right, so let's take a look at the next one. Got PBr3. That's our phosphorus tribromide. We'll do the same starting material. Just like before, we said that this is a bad leaving group. We're going to treat this with phosphorus tribromide. Again, phosphorus tribromide is a really, really good electrophile. So this oxygen will attack the phosphorus and kick off the bromine. And in this reaction, the bromine can steal back this proton. At least that's how the book shows it. And we end up making HBr. Oops, sorry. I'm skipping a step. Leave this as is. In fact, that equilibrium wouldn't be very favorable. I apologize. Scratch this. In this step, we'll actually leave that proton on there because it's already a good leaving group at this point. This entire thing can fall off as a good leaving group. And just like before, this is an SN2 style reaction. And you end up with your final alkyl halide. So this one is a little less steppy. You don't need to deprotonate before the bromide attacks back in. Does that make sense? Really, this is just adding to our toolbox. Oftentimes, if we go back up and we look at those review reactions, those were pretty harsh conditions. If you have a starting material that can do other acid-base chemistry, you probably don't want to huck in HBr, right? That'll do maybe addition of a bromine across a double bond, things like that. So you have to use alternate routes like PBr3 if you have competing side reactions that can occur. All right? So that was our substitution review and 2 new reactions. Let's take a look at elimination super briefly. This is going to be a quick review. So let's take a look at E1 chemistry with alcohols. Let's say I want to go from this tertiary alcohol to this alkene. What reagents would I need to do an E1 elimination?
Sulfuric acid.
Yeah, catalytic acid. Usually it's catalytic sulfuric acid. You don't want any water here, right? Because that will actually favor formation of the starting material, not our product. So catalytic acid, and then do we want this hot or cold?
Hot.
Hot. So catalytic acid and heat will favor this. We saw that in our dehydration of cyclohexanol, making cyclohexene. This works for secondary alcohols as well. And then for the other one, if we've got a primary system, we can make an alkene, but we need to convert that alcohol to a good leaving group. So what should we do to convert the alcohol to a good leaving group?
Tosyl chloride.
Yep, tosyl chloride and pyridine. And then once that's a good leaving group, we want to pick a non-nucleophilic base because we don't want it to do SN2, right? So what would be a good non-nucleophilic base?
NaH.
NaH, DBU, DBN, tertbutoxide, one of the ones we covered last term. So I'll just pick one. Let's do DBN. Any one of those non-nucleophilic bases. You can't use sodium hydroxide because that'll just take you right back to your starting material, right? It'll substitute it off. We don't want that. We want the elimination. So make sure in this one that you use a non-nucleophilic base. If you are a little rusty on this, there's no shame in that. Just go back and review Chapter 8. Unfortunately, the very nature of organic chemistry means we can't really forget very much as we go through the year. So if you do feel rusty on older stuff, just go back and flip through those chapters. You'd be surprised how quickly it'll come back to you. All right. So now we got to get into some different chemistry. We've already done reduction, we've done Grignard reactions, we've done substitution, elimination, but we haven't done oxidation yet. So let's take a look at oxidation reactions of alcohols. And I'll show you this general scheme. I'm going to color code it to show a blue hydrogen coming off there. All right, which way is reduction, going left to right or right to left? Is it the upper arrow or lower arrow? That's another way.
It's the lower one.
It's a lower one, right? We have already seen how to take an aldehyde, ketone, ester, carboxylic acid back to the aldehyde. So the lower one is a reduction. So I'll just call this red as an abbreviation. And are we gaining or losing electrons? We're gaining electrons. All right, that means the top one, conversely, must be an oxidation reaction where we lose electrons. All right, really quickly, what's the oxidation number for that central carbon? Remember, carbon's more electronegative than hydrogen, just barely. So valence is always going to be 4 for carbon. If we think about a carbon-carbon bond, that's a tie, so it gets one of those. So I'll show one. One of these. It'll get both of those because it's more electronegative than hydrogen. However, it doesn't get any between the carbon-oxygen bond, right? So 4 minus 4, 0. All right, makes sense. All right, what about this one? It's still going to be a valence of 4, but how many electrons? 2. So it'd be positive 2 for this one. So for this specific oxidation, we're losing 2 electrons, right? And if we're doing the reduction, we're gaining 2 electrons. So it depends which direction you're going, and it is important to pay attention to this overall process. So let's take a look at the elementary steps that we can take. And we'll start with primary alcohols. And I really like to color code the hydrogens coming off the central carbons too, so I'm going to show all of those as blue. So we know a primary alcohol is attached to one other carbon, then it's got 2 attached hydrogens, right? So this is a primary alcohol. All right, what's the oxidation number for that central carbon?
0.
It'd be -1, right? So you can go back and check, but it would be -1 for that central carbon. All right, in these oxidation steps, typically what we're going to do is oxidize. And it's going to be a 2-electron oxidation. Another way of thinking about it is when you do a 2-electron oxidation, you're going to lose one of those blue hydrogens, right? So if we do that, we're going to lose one of these hydrogens, and we'll have that. Now we've got an aldehyde. And the oxidation state, if we're gaining 2 electrons, must be +1. All right, and we can do this again, and we can say, all right, let's oxidize it again. 2-electron oxidation. In this case, we're going to lose another blue hydrogen. And the question is, what will swap it out? In this case, it'll be an OH. So we can go from a primary alcohol to an aldehyde to a carboxylic acid. What do you think the oxidation number is going to be for this one? +3, right? So if you do a 4-electron oxidation of a primary alcohol, you'll go all the way to the carboxylic acid. That takes a lot of power to do that much oxidative chemistry. If you've got a weaker oxidant, you can actually stop at the aldehyde. So we have to be careful about what reagents we choose, depending on where we want to end, right? If we pick a gentle oxidizer, we'll get the aldehyde. Strong oxidizer will overshoot, be uncontrollable, and you'll end up at your carboxylic acid. Okay, let's do the same thing with secondary alcohols. Okay, secondary alcohols, we know, look pretty dang similar. However, this time we only have one blue hydrogen. So I'll do oxidation down here. And again, we'll do 2 electron steps. This is our secondary alcohol. And in this case, its oxidation number be 1, 2, 3, 4. That means it would be 0. What do you think our product will be from a 2-electron oxidation, following the same trend as above? What functional group will we make? Ketone, absolutely. And we go to an oxidation state of +2. Do you think we can oxidize this anymore? Let's go and look up here, right? We said in each of these oxidation steps we lost a blue hydrogen. If you go down here, we're already out of blue hydrogens. So we're done at this point. We can't go any further and oxidize this anymore. It's exhausted. All right, so let's take a look at the next one. Tertiary alcohols. And again, just be thorough. You know the oxidation here is going to be +1. All right, what product do you think we'll get out of this?
I don't think so.
Trick question, right? No reaction. We don't have any of those blue hydrogens to lose, so this will just stare at your oxidant and wonder why you're trying it. All right? So this is important to remember. Primary alcohols you can convert to an aldehyde or a carboxylic acid. Secondary alcohols you can only convert to a ketone. And tertiary alcohols don't do a dang thing. They just sit there. It's important to remember that. All right, so now the question is, what reagents do we need to do these oxidation steps, specifically with primary and secondary alcohols? We need to be very specific with primary alcohols. Like I said, strong oxidants will always overshoot to the carboxylic acid. Gentle ones you can stop at the aldehyde. So let's take a look at the oxidizing agents. In this chapter, I'm going to be perfectly honest, bugs me, so I'm going to show you some alternate reagents. So the first one, you use Chromium Trioxide, that's CrO3, sulfuric acid, and acetone. When you do this, you can make chromic acid, or if you don't have chromium trioxide, you can use sodium dichromate, which is an analog that looks way more complicated. Sorry, that's the sodium right there. They moved the screen on me. Oops, there should be an oxygen in between. And you can actually go to that same chromic acid by using sulfuric acid and water. This is chromic acid. And it was used traditionally as a strong oxidizing agent. People oftentimes avoid drawing out the sodium dichromate too by just writing Na2Cr2O7. It's a lot easier to write than that big long chain. But chromic acid is a great oxidizer. And it causes cancer. It's one reason I don't like this section in the textbook. Most chemists would look at you a little funny if you said, I'm going to do a chromic acid oxidation, because it is not environmentally friendly. Hexavalent chromium is related to all sorts of terrible diseases. Back in the 50s, when they first were developing this stuff, they were pretty cavalier with the chemistry that they did. And unfortunately, a lot of the chemists that did a lot of this work ended up dying prematurely from pancreatic cancer, liver cancer, you name it. They got really sick. So I show it to you because it's a historical thing. You'll see it a lot in textbooks. It's just kind of stuck around for a long time, but we're not going to get into the mechanism. It's not worth our time. So let's kind of leave that at that. Let's take a look at some example reactions. So let's say I've got this alcohol, and we know we've got a blue hydrogen right there. And we treat this with sodium dichromate, so that's Na2Cr2O7, sulfuric acid, and water. What do you think we're going to get out? Just based on our last lecture notes. We're not going to get an alcohol. Are we going to get an aldehyde, carboxylic acid, ketone? What are we going to get? Ketone, right? We're going to pluck off that blue hydrogen. We're going to end up with a ketone. Just like we saw before, primary alcohols, the only place you can take them when you oxidize them is to a ketone, at least that we know of right now. Make sense? Let's take a look at a slightly more complicated one. Oh, sorry, secondary. Thank you. That's why I keep you guys around. Keep me honest. All right, let's do another one. This one's our primary alcohol. We're going to use the same reagents. This time I'll switch them up to the other one. So CrO3, that chromium trioxide, sulfuric acid, and acetone. All right, if this is a really, really, really strong oxidant, what do you think our final product is going to be? What do you guys think? Carboxylic acid. Like I said, if you've got a strong oxidant and it's going to blow way past your intermediate, you could say, well, theoretically, our first intermediate of this reaction is going to be this aldehyde, right? With one of those on. Problem is you can't isolate this. And that's because your oxidant is too strong. Instead, what you're going to do is you're going to overshoot and go all the way to your carboxylic acid. Does that make sense? All right. So I'm going to briefly show you a little bit about this mechanism. We're not going to go too far into it because, like I said, this is very dated chemistry. However, there might, hint, be a sapling problem where they ask you about this. All right, so in this mechanism, we'll use a secondary alcohol. This time, I'll name it, right? And we've got chromic acid. When you mix these two together, you end up with an equilibrium reaction, and you generate something known as a chromate ester. And then in your next step, water is going to act as a really weak base. And it's going to steal that blue hydrogen, or specifically blue proton. We saw we always lose one of those in an oxidation reaction. You do this, we'll clamp down, kick this off. You'll end up with your ketone. And you'll end up with your chromate anion. But this chromate ester, I believe there is a question on sapling that asks you to draw it, so I did want to show it to you. Make sense? So then the question is, well, what if we don't want to always go to the carboxylic acid? What if we do want to hit that intermediate, the aldehyde? That's an important reaction. And there are a bunch of different ways to do this. But we need to use a gentle oxidizer. The first one is called Pyridinium chlorochromate. This was the first one that was really developed. It was developed on accident, actually. And what you do is you take pyridine, that's the base that we've seen used quite a few times. They mixed in chromic acid, not knowing that they were making this, and HCl. What they did was accidentally make a new oxidizer that has a little less power than the chromic acid one. Looks like this. Most people will just refer to this as PCC rather than pyridinium chlorochromate because it flows off the tongue a little bit better. So that's one of our oxidizers that's really gentle. Let's take a look at this and say, all right, if it's a gentle oxidizer, and I've got this alcohol, and I react this with PCC, the pyridinium chlorochromate that I just showed you, what do you think we'll get? The aldehyde, right? We're only going to remove one of those blue hydrogens. Let me keep my color coding the same. So it's important to know that this stops at the aldehyde. Again, the main problem with using this reagent is it will still give you cancer. Anytime you have chromium with 6 bonds on it, it will give you cancer. So again, this is phased out. It's not a common reaction. It's just a historical artifact that you'll find in the ACS exam and all throughout the textbook. So I feel like it's my obligation to show it to you guys. So then the question is, what reagents can we use that won't give us cancer? And we do have a few ones. How many of you got the 3rd edition of the Klein textbook? A couple people? So in the 3rd edition, he actually introduces these. More environmentally friendly ones. If we look at the more environmentally friendly oxidizers, we've got a few different types. The first one is called the Swearin Oxidation. And with the Swearin oxidation, you can again take your primary alcohol and you can react it with a set of reagents and get it to stop at the aldehyde. The problem with this reaction, and I'll show you in a minute, is it puts off this gas, the sulfur-containing gas. How many of you guys know what sulfur smells like?
It's nasty.
It reeks. When somebody runs this in the lab, it's usually powerful enough to make people leave for the day. It is crazy pungent. However, it's a nice reaction because it doesn't give you cancer. So it's a good alternative. In order to do the Swearin oxidation, you do have to be careful with your set of reagents. Typically what you use is something called oxalochloride, DMSO as your solvent, or actually it's both solvent and reagent here. You normally run this in dichloromethane and it needs to be run incredibly cold. So oftentimes they'll run this reaction in a dry ice acetone bath. Like I said, it's a very stinky reaction. It's a little hard to carry out because you have to keep it super duper cold, but it works really well because you're not exposing yourself to these horrible chromium metals. So that's one of the more modern ones. So again, this stops at the aldehyde. The other one is called Des-Martin periodinane. And again, if we look at this reaction, you can take a primary alcohol, react this with DMP, that's the abbreviation for Des-Martin periodinane, and this will give you your aldehyde directly. Again, this reaction is not perfect. And I'll show you guys why. This is explosive.
No oxidation reaction.
But it does stop at the aldehyde. Yeah, and it's a little bit more environmentally friendly. People will often say, well, why would you ever use an explosive reagent? It all depends on the scale, right? If you're doing a little itty-bitty reaction and you're using a tiny bit of Des-Martin periodinane, the chances of it causing any significant problems are pretty minimal. If you're working in a chemical production facility and you want to make 2,000 metric tons of a compound and they say, oh, let's try using DMP, your boss would say, no. You will likely blow up the plant. So you have to be very careful with the one you select, but this one doesn't stink and it works really well. There are a bunch of other oxidation reactions. I showed you guys in lab a more modern one for benzyl alcohols to stop at an aldehyde. That one's incredibly green, non-explosive, doesn't give you cancer. So there's a huge amount of research out there about these oxidation reactions, but these are the most classic ones that are on the market today. I don't think I'm going to show you guys the mechanism for that. These two, at least. If you are really curious about them, you're more than welcome to go through the textbook. They're pretty steppy and a little bit beyond what I expect you guys to know, but they are related to a lot of more modern organic chemistry. All right, so we've got a few more minutes, so let's do a couple practice problems before we head out.
Is there a preferred answer than one when it comes to choosing?
No, pick your poison,
Okay.
literally.
Yeah.
All right, so let's take a look at this unique example. Oops, sorry, this should be an alcohol here. And I'm going to use PCC, the not super friendly one, just because it's the one you're most likely to see in your textbook and online. All right, if we look at this one, the question is, what product will we get out of this reaction? And remember, PCC can do a 2-electron oxidation, but not a 4-electron oxidation. And assume you have excess of your PCC too. Like I said, I really like drawing in the blue hydrogens attached to the carbon. So let's focus on this one on the left-hand side. We're going to pluck one of those off. So what functional group do you think we'll get for that left-hand side? An aldehyde, right? So we'll form a carbon-oxygen double bond. One of those blue hydrogens will still hang out there. And then what about the oxygen on the right-hand side? What will that turn into? Ketone, right? So this does throw people. They'll say, I thought PCC always makes aldehydes. It always makes aldehydes for primary alcohols, but if you have a secondary alcohol, it'll still do a 2-electron oxidation and give you a ketone. So it is versatile in that regard. So be careful of that. What if we had a tertiary alcohol in here? Nothing would happen, right? So it is important to remember PCC does 2-electron oxidations. Tertiary alcohols don't do a thing.
Is there ever like can you remove the proton off of the oxygen at some point and then like do like a hydride shift?
Not quite. You don't see hydride shifts like that. That was a good question, though. All right, so let's take a look at one last thing. The textbook has a whole section on oxidation of phenols and bioredox reactions. I'm going to essentially scrap that from our lecture material because I feel like it doesn't contribute that much. It's related to biochemistry, so if you do plan on taking biochem, I would recommend reading through it, but it doesn't help us a lot in terms of what we need to know for synthesis. So you're welcome to read through that section or watch the Khan Academy video. And then last but not least for this chapter, they've made a good summary of reactions at the end of the chapter. I would recommend trying to expand on your reaction map, drawing more arrows. However, be very careful with some of these transitions, right? So, for example, if you're making an aldehyde or a ketone, be specific now. Is this making an aldehyde, or is it making a ketone, or is it making a carboxylic acid? We now have the ability to control which one we're making. So I would recommend adding that. If you want to fill in the blank study guide, I put one on here, but I really like just making my own reaction maps. If you need to do this just to remember reagents, you can do that as well. So that's where we're going to stop today. Remember that we do have a quiz coming up and sapling. If you guys have any questions on sapling, you're always welcome to email me and I can help you via email.